invitation to the organizers. So I'm the last talk of the session, so I don't have to introduce much about this topic, which is spin charge interconversion in antiferromagnetic-heavy metal barrier systems. So it's a very hot topic in spintronics. What ultimately limits the speed with which we can perform this conversion is the speed with which we can generate a non-equilibrium spin in the spin source, which is the magnet. Now, recently, there has been a number of works on this topic in which this non-equilibrium spin population has been induced via the coherent excitation of magnons via an optical pumping effect. And here, the circular polarization of the optical pump or a magnetic field have been used to lift the degeneracy between the two opposite spin magnon bands and therefore induce a net spin accumulation and a net spin transfer. Now, more recently, also some works have shown the possibility to spin pump by using a linearly polarized optical pulse. And in this case, the effect has been associated to an impulsive stimulated Raman scattering effect, or as Roman told us in the first talk of this session, to a magnetostrictive type of effect. Now, if the speed is limited by the dynamics of the magnetic source, the efficiency with which we can perform this spin charge interconversion depends on how well the spin source, the magnet, talks to the spin to charge transducer, the heavy metal. And this is determined by the type of interactions that occur at the interface between the two elements, how strong these are. Now, this is in the experiment I will introduce today, we have really focused on this interface region. And the reason why we could do that is because in our mechanism, both the onset of the non-equilibrium spin and the spin transfer to the heavy metal rely on the same type of physics, on the same type of interactions. So this enormously simplifies the physics, allowing us to develop a microscopic understanding and therefore pin down the phenomenological parameters that are most important for determining this spin transfer efficiency. The layout of our experiment is common to what has been used by other groups. We use optical pumping to drive the bilayer system out of equilibrium. Any spin transfer that results from this non-equilibrium condition is collected by the heavy metal element and transformed into a fast current pulse, which makes basically the heavy metal behave as an antenna and emit electrodipole emission, which we then detect in the bandwidth that goes from 0.3 to 3 terahertz by using electro-optic sampling. So the amplitude of this terahertz emission is directly proportional to the spin, to the injected spin, so to the spin pumping, and we can have a direct measurement of it. Okay, so the mechanism that we rely on to generate this non-equilibrium spin in the antiferromagnetic insulator is the picosecond Spin Seebeck effect, which is a mechanism that has already been studied in ferromagnetic insulators, but not in antiferromagnetic insulators. So in this case, when we pump with an optical pulse, the great part of the pump energy is absorbed by the heavy metal, and it's used to heat up the free electrons of the heavy metal to an effective temperature, which is higher with respect to the ambient temperature. Now, after this, these hot electrons start to thermalize with the environment, in particular with the antiferromagnetic insulator, and the processes with which they thermalize with it, which is fast enough that we can detect them, are direct electron-magnon interactions. So essentially, there are two types of scattering that can occur. Spin flip scattering that results in the emission of a magnon with opposite spin polarizations. The reason why we can have these two scatterings is that the heavy metal, to start with, is spin polarized, but also the antiferromagnetic insulator has two magnon bands that are degenerate in spin. So the probability of these two scattering events, which result in the emission of opposite spin magnons, are equal. In order to lift this degeneracy and therefore have a net spin accumulation in the antiferromagnetic insulator, and we need to break the degeneracy, for example, by applying a magnetic field. Now, things are different for a magnetic insulator because obviously the magnonic bands are spin polarized. So we start with a situation in which the probability of these two scattering events is different to start with, and we don't have to apply a magnetic field. Okay, so then you understand that the efficiency of this communication basically relies on the strength of this scattering event, which is parameterized by the exchange interaction between the spin of the free electrons on the heavy metal and the localized spins on the antiferromagnetic insulator side. Now, if we consider this exchange interaction weak with respect to the strong exchange interactions internal in the antiferromagnetic insulator, then we can calculate the pumped spin in a mean field approximation by using golden Fermi rule. Basically, what we do is to integrate over the magnon states, which represent the final states in the scattering, a scattering probability. So this here represents a scattering probability. We have two different integrals which describe the two possible scattering events that we can have. They have opposite sign with respect to each other because they result in the emission of an opposite magnon and therefore in an opposite spin pumping. What we have here is the density of states of the magnons. We have NB, which represents the boson-Sen distribution of the electron hole pair in the heavy metal, and alpha and N beta represents the instantaneous distribution of magnons. Alpha and beta indicate the two magnon bands in the antiferromagnet. And then we have another parameter, which is μs here. μs represents the accumulated spin in the heavy metal that results from the spin pumping, because we have seen that these scatterings obviously are responsible for inducing the spin accumulation in the antiferromagnetic insulator, but they're also responsible for the spin transfer from the antiferromagnetic insulator to the heavy metal. So as soon as we generate a non-equilibrium spin on the antiferromagnetic insulator side, this spin then is pumped back in the heavy metal and induces a spin accumulation, which we describe with μs. Now, the reason why μs appears here is that it acts on the spin pumping as a sort of feedback mechanism. Because if we start with a spin polarized population on the heavy metal, obviously we are already making one of these scattering events more probable than the other. So this μs acts by increasing the probability of one scattering event and decreasing the other one. And that's why it appears with a plus or minus sign. Now, the extent to which this feedback mechanism is important depends on the relative time scales between the scattering time and the spin lifetime in the heavy metal, which has been characterized by other equilibrium studies. It's in the range of 10 femtoseconds, so comparable or higher with respect to the spin flip scattering time. So it needs to be considered, we think. Okay, so now let's go to the details of the experiment. To do this experiment, we worked on two selected materials, antiferromagnetic insulators, that belong to the same family of 3 fluoride perovskites, potassium cobalt fluoride and potassium nickel fluorides. Now, these materials were very well known in the 60s because they were studied as the prototypical 3D Heisenberg antiferromagnets, especially potassium nickel fluoride. In potassium cobalt fluoride, a higher spin-orbit coupling results in a small tetragonal distortion below the nail temperature. But this is a subtle one, which does not seem to impact, to result in a significant anisotropy in the magnon bands. Now, we see here that these materials have a perovskite structures, and they are absolutely identical from the magnetic point of view or the crystallographic point of view. Here we have that neighboring spins are opposite and can point in any one of the 3 cubic directions, the 1, 0, 0, the 0, 1, 0, or the 0, 0, 0, 1. So in principle, we can have 3 types of domain with the nail vector aligned along one of these 3 directions. Here we show some squid measurements where we have characterized the nail temperature, which is 117 in potassium cobalt fluoride and 245 Kelvin in potassium nickel fluoride. Now, an important difference between these two materials, which is significant for the experiment we want to carry, is the fact that despite belonging to the same magnetic point group and having very similar magnetic and crystallographic characteristics, they have a very different magnon gap at the center of the Brillouin zone. Now, this has been measured by Davide Bossini. I should have shown a picture of him, but I'm too kind, by using pump probe measurements. And then you see here, as a function of temperature, while in potassium nickel fluoride, we have a gap of about 97 gigahertz, which obviously decreases towards the nail temperature. In potassium cobalt fluoride, we have a gap that is an order of magnitude higher, around 1.1 terahertz. Okay, before I go into the details of the experiment, just want to comment on the magnetostatics a little bit more. Another reason why these materials are particularly interesting to us is the fact that they have large magnetic domains, and these domains can be made even larger by applying a relatively small magnetic field. When a field is applied along the vector, we don't have a spin-flop transition, but rather we have domain wall motion that promotes those magnetic domains that have the nil vector in the energetically more favorable position perpendicular to the magnetic field at the expenses of those that have the nil vector aligned with the magnetic field. Now, at the field at which this domain wall motion occurs is much lower than the spin-flop field. So it's about, we have characterized this with squid measurements. It's about 3.5 Tesla in potassium nickel fluoride and 0.5 Tesla in potassium nickel fluoride. Now, in our setup, we can apply 0.8 Tesla. So we expect that the spin pumping in potassium nickel fluoride will predominantly come from one type of domains, while in potassium cobalt fluoride, we will keep a multi-domain state. But it's not so significant from the magnetodynamics point of view. This is a textbook graph of the different modes we have in a uniaxial antiferromagnet, to which we can approximate our cubic antiferromagnets in the small oscillation limit. And with the magnetic field parallel or perpendicular to the easy axis, we have that a gap is present at zero field. And this has been also characterized in potassium nickel fluoride. For a magnetic field perpendicular to the nil vector, we see the gap at 97 gigahertz as we would expect. Okay, so these are the measurements. So these materials have both been grown by a floating zone technique. We have polished the surfaces and sputtered 5 nanometers of platinum on both of them. Now, for these two antiferromagnetic insulators, we use two different pumping configurations. And the reason is that the central wavelength at which we're pumping is 800 nanometers. Now, this wavelength corresponds to a transparency window in potassium cobalt fluoride, but it is characterized by a pretty high absorption in potassium nickel fluoride. Because we want to maximize the energy absorbed by the heavy metal, because that's what triggers basically the spin pumping, then in the case of potassium nickel fluoride, we privilege a flipped geometry in which we pump directly on the platinum side and measure the terahertz on the other antiferromagnetic insulator side. Okay, so first let me show you three elements that tell us that the terahertz emission is generated by the inverse spinel effect in platinum. Now, the first piece of evidence is that if we repeat the measurement without the platinum or without the antiferromagnetic insulator, we see nothing. So we need both elements, the magnetic source and the spin-to-charge transducer, to see something. The second piece of evidence is that is in the polarization of the terahertz emission, which is perpendicular to the applied magnetic field. In all our measurements, we're applying a magnetic field in the plane of the interface along the 100 axis. The terahertz emission is perpendicular to it. And this is aligned with the symmetry of the inverse spinel effect for a pumped spin current parallel to the magnetic field, as we would expect. The third piece of evidence is that if we flip the pumping geometry, we have a flipping in the terahertz emission. Although the Ziegler is smaller due to the higher absorption, we have a flipping in the terahertz, terahertz emission. And this is also in agreement with the symmetry of the inverse spinel effect, because when we flip the device with respect to the pumping direction, we are effectively flipping the direction of the spin current, which is always going from the magnetic source to the heavy metal. So by flipping JS, obviously, we expect a flipping in JC, and therefore a flipping in the terahertz emission. Okay, so now I want to give you, now that we have established that the terahertz resides in the origin of the terahertz emission resides in the inverse spinel effect, I want to give you three signs that the spin pumping is caused by the picosecond spin Seebeck effect. Now, the first sign is that we have no dependence on the polarization of the optical pump, which makes us think that what we are observing is a thermal effect rather than being some other optical effect. Now, the second evidence is in the dependence of the terahertz emission on the magnetic field. So as I said, in order to observe a net, to induce a net spin accumulation in the antiferromagnetic insulator, we need to lift the degeneracy between the two magnon bands, and we do that by applying a magnetic field. And indeed, what we see is that at zero field, we see 0 terahertz emission, and then we see a linearly increasing terahertz emission as we increase the value of the field. Now, the opposite sign in potassium nickel fluoride with respect to potassium cobalt fluoride is due to the flipped geometry that we're using, as I said at the beginning. Now, this is very different from a measurement done in YIG by using the same experimental layout, in which you see that the terahertz emission has a completely different magnetic field dependence and obviously follows the magnetization, and it has the same hysteretical behavior as the magnetization does. Okay, so the third element is the temperature dependence of the terahertz emission. Now, the first striking observation that we make is that the temperature dependence of the terahertz emission is very different in these two antiferromagnetic insulators. And there are two main differences. The first obvious one is that while in the potassium nickel fluoride, the terahertz emission keeps increasing as we decrease the temperature, in potassium cobalt fluoride is characterized by a peak at the net temperature, followed by a decrease. The second difference is in the fluence dependence. So while in potassium nickel fluoride, we have no fluence dependence as a function of temperature, in the case of potassium cobalt fluoride, we have a pretty strong fluence dependence below the net temperature. Now, to understand these results, we need to consider, again, the microscopic model. And we need to understand the probability of this scattering event that triggers the spin pumping. Now, as we go down below the net temperature, at low temperatures, we have the opening of a gap in the magnon density of states. So in potassium cobalt fluoride, this gap we said is about 1 terahertz, a little bit more than 1 terahertz, and it becomes commensurate with the energy of the heated electrons. So the overlap between the distribution of electrons on the heavy metal side and the magnon density of states on the antiferromagnetic insulator side is reduced. And this obviously reduces the probability of the scattering. As we go up in temperature towards the net temperature, the gap is reduced, the overlap between the two density of states becomes higher, and therefore we start having enough electrons with a sufficiently high energy to excite magnons. So the reason why we see a reduction in the signal in terahertz emission below the net temperature in potassium cobalt fluoride has to do with the fact that there are not enough electrons with sufficient energy to excite magnons above the gap at low temperatures. Okay, these also experimental results have been compared to the theory based on the microscopic modeling I've just told you about, and we see good agreement, both in the fluence dependence and in the presence of this peak at the net temperature. What about potassium nickel fluoride? Now, in potassium nickel fluoride, the band gap is significantly smaller, an order of magnitude smaller. So we don't have the same impact on the spin pumping that we had in potassium cobalt fluoride caused by the opening of the gap. Instead, to understand these results, we may compare them to results that we have available for another completely different material, a ferromagnet, a ferrimagnet, YIG. If we plot the 2 terahertz emissions as a function of temperature in these two materials that are completely uncorrelated, as a function of the normalized temperature with respect to the Curie temperature in YIG and the net temperature in potassium nickel fluoride, we see a pretty good overlap between the two curves. So this makes us think that this temperature dependence doesn't reside, for example, exclusively in the platinum layer, but has to do with the onset of long-range magnetism. So it is to be associated with the exchange interaction between the free electrons on the heavy metal side and the localized spin on the antiferromagnetic insulator side. Now, the temperature dependence of the picosecond Spin Seebeck effect and the normal slow Spin Seebeck effect has been extensively used in, studied and characterized in YIG. we have ourselves done the measurements of the picosecond Spin Seebeck effect at low temperatures in YIG, and we have seen a temperature dependence that goes like T to the third, which basically joins up with the temperature dependence observed by the group of Tobias Kampfert in the higher temperature range. If we go in the slow type of measurements of this Seebeck effect, what we see is that at low temperature, the behavior is very different from what we measure with this optical terahertz emission method, because it's characterized by a peak. But this peak has been associated to the spin transport properties of bulk magnons. Bulk magnons, in our case, do not contribute. We're really sensitive to surface interface effects. And indeed, what we see is that these temperature behaviors can be rather overlapped with the temperature behavior of this low Seebeck effect observed in the higher temperature range, where magnons have a shorter diffusion length, and therefore magnons that are closer to the interface contribute more to the spin transfer. So here we have a larger contribution from the interface effects, even in the slow measurements, and everything seems to agree. Okay, so before I conclude my talk, I want to just spend a few words, because we've seen the pump probe measurements that Davide did in Nijmegen, that in principle it is possible to excite coherent oscillations in these materials via optical pumping. So do we see coherent oscillations? Yes, we do see coherent oscillations, so unfortunately they were an artifact. So these are the measurements done in Nijmegen by Davide. We saw very nice oscillations here, which did not depend on the magnetic field. They had a dependence on the polarization of the optical pump, so they flipped sign by going from horizontal to vertical polarization. And the striking thing, this was a very subtle artifact, because the striking thing is that they had a temperature dependence as well. These oscillations were pretty much damped towards the nail temperature, and they had a peak at 1.2 terahertz, exactly where we pretty much were expecting the frequency of our coherent mode. So as you can imagine, it took us a while to understand that this emission was coming from the windows of our cryostat, not the antiferromagnet. And it took us a while to debug. It was quite frustrating, but after we substituted the windows with a different material, we eliminated this artifact, and we were able to isolate the nice picosecond Spin Seebeck effect that I've told you about. Okay, so let me conclude. I've shown you a way to optically excite generate incoherent spin pumping from antiferromagnetic insulators to platinum. And I've shown you that this is due to the picosecond Spin Seebeck effect by showing you temperature dependence measurements and magnetic field dependence measurements. And I've also shown you that the efficiency of the spin transfer in antiferromagnetic insulators heavy metal structures is heavily impacted by the opening of the gap in the magnetic density of states. So this is something that should be taken into account when doing these studies. With this, I would like to thank all the collaborators that worked on this project, Joe Barker, which developed the theory, and Roman Pisarev, which gave us the materials, and of course, Davide Bossini, that contributed in many different ways, and first of all, the people on Cambridge, which did the measurements, particularly Farhan Khalid and Dominic Amara. Thank you for your attention.